Okay, this discussion is going to be over kinetic molecular theory and some of the calculations we can do based on that, and Graham's law, and how we deal with, quote, real gases. Okay, kinetic molecular theory, we're just going to go over the postulates again. We talked about them in an earlier discussion. Basically, kinetic molecular theory, which explains why gases behave as they do, assumes that the volume of individual particles is zero or negligible compared to the volume that the gas occupies. The other thing, and this is an important one to keep in mind, okay, so we're going to we'll start by this one, because this is an important thing to think about when you're answering conceptual questions about the behavior of gases. Is just always think about, when we're talking about pressure, we're talking about the frequency of the collisions of the gas particles with the container walls. Okay. Then the other assumption that we make is that the particles do not exert any kind of repulsive or attractive forces on each other. And then the last one, and this is another one that I would mark as a really important one to keep in mind when you're answering conceptual questions about the gases, is that the average kinetic energy of the gas particles is proportional to the Kelvin temperature of the gas. So gases at the same temperature, the particles will have the same average kinetic energy. And so we're going to look at some equations that are related to kinetic molecular theory. And the first one that you'll see is that the average kinetic energy is equal to 3/2 the gas constant times T. All right? And so this is, again, sort of a quantitative expression related to that fourth postulate of the kinetic molecular theory. The thing to realize in here, and we haven't talked about this before, but that this R, this gas constant, has another value that we're going to be using. And the way to determine which value of R that you're using is basically this value of R is used when you have something related to energy. All right, we'll be using it a lot in Chapter 6, where we're going to be talking about thermochemistry. But here, anytime you have an expression where you're talking about energy and it involves this gas constant, the constant is 8.3145. If it involves pressure, then you're going to use the 0.08206 value. All right, and this particular expression, just in case you're interested, you can find how this expression is derived. Usually in most physics texts, you don't really see a very thorough derivation in chemistry textbooks. Another expression that you'll see is the root mean square speed, and this is just a way of measuring the average velocity of the gas particles. And again, U is used for the average velocity, and it's equal to 3RT divided by M. And the key thing to remember here, again, is that the R here, since we're talking about some kind of energy-related thing, is 8.3145. The other thing to notice is that your M, which is your molecular mass, is in kilograms in this equation. Now, we're not going to do any example problems with regard to the kinetic energy equation that we just looked at, or this root mean square speed equation, and that's mainly because they are kind of plug and chug type problems. And so as long as you know what units you're supposed to put the values in at, these are pretty straightforward calculations. And so I'm not going to spend time here in this podcast talking about those types of calculations. Okay, now let's move on here. We've got two new terms we're going to look at. The first one is diffusion. This describes the mixing of gases. One of the characteristics of gases is that on their own, they will basically disperse themselves. If I am sitting at the front of the classroom and I open a bottle of ammonia, and we did not have any kind of forced ventilation in the room, the people at the back of the classroom would still eventually be able to smell the ammonia. And that's just because you have random motion of gas particles basically disperses them, even in the absence of some sort of forced ventilation type movement. Okay, so just their random motion is going to disperse them, and that's called diffusion. The other one is effusion, and this is where we have gas molecules passing through a small hole into an evacuated chamber, or a chamber where it has a lower pressure. It kind of has a vacuum on it. So here's kind of an example of effusion. So we have the gas particles over here bouncing around, and basically, based on their random motion, okay, they will eventually, run into this hole and hit it just exactly to where they're able to pass through the pinhole into the vacuum area. And then here's a pictorial example of diffusion. All right, and this is a pretty classic experiment here where I have a cotton swab saturated with hydrochloric acid and another cotton swab saturated with ammonia. I put them at opposite ends of a tube. All right, and so you see that we have just random motion of the hydrochloric acid, random motion of the ammonia. We're assuming that they're at the same temperature, and at some point they would meet, and they're going to form an ammonium chloride precipitate at the point where they meet. And as you can see here, and we're going to talk about this in just a minute, that the ammonia would travel much farther than the hydrochloric acid would in the same amount of time. Okay, and that relationship, the fact that the ammonia, which is a smaller molecule, would travel faster when it's at the same temperature than the hydrochloric acid molecules would, is called Graham's law. And what he observed is that we're talking about effusion, that the rate of effusion for gases, the ratio of their rates is inversely proportional to the square root of their molecular masses. And then we have a similar thing for diffusion, where the distance traveled by a gas, that ratio of their distances traveled, is again inversely proportional to the square root of their molecular masses. This is a really useful relationship, and so we're actually going to do some sample calculations with this. Well, where did my example problem go? Okay, I guess we'll do it at the end. I thought I had a sample problem in here. Okay, let's skip ahead to real gases, and we'll talk about that. Maybe I just got my slides out of order. All right, real gases. Remember, we talked about how ideal gases are gases that behave according to the kinetic molecular theory. Well, real gases are ones that basically are in some sort of set of conditions that prevents them from behaving this way. And the key things we have to look for, where we have to vary, or where the use of the ideal gas law is not appropriate, are when we have conditions of high pressures and low temperatures. Okay? And basically what happens is there are two basic assumptions of kinetic molecular theory that basically are not valid at high pressures and low temperatures. One is, the thing to remember is that at high pressures we typically are talking about small volumes and high concentrations. And under those conditions, the volumes of the molecules do become significant. So we cannot say that the volume of the molecules is negligible relative to the volume that the gas is contained in. So that's one part of kinetic molecular theory that would not hold at high pressures, for example. And the other thing is that at high pressures and high concentrations, and also at low temperatures, these attractive forces between the molecules do become important. High pressures, we have lots of gas molecules that are at very close proximity to each other. And so attractive forces will play a role in the behavior of the particles. Same thing with low temperatures. At low temperatures, they have low kinetic energy, and so the influence of attractive forces on the paths of the gas particles, again, become important. We cannot just say that they are negligible. All right, so here, as you can see, if you think about pressure as being the frequency with which the particles hit the wall of the container, if you look at low concentrations, we have very few other molecules that are able to interact with our gas particle that's going to hit the wall. Whereas at high concentrations, we have a lot of particles that are present that can potentially interact and can affect the path of the gas particle and thus affect the frequency that it collides with the container wall. Okay, and same thing here, just a different sort of view. If we compress them, we have higher concentrations, they're going to interact more with each other. And also, as you can see between these two examples, that the volume of the actual gas particles here does make up a significant part of this total volume in which the gas occupies. So the actual volume of the gas particles becomes significant as well. This is a graph basically showing you what's going on as far as this deviation from ideal behavior. With ideal behavior, we have ideal gas law, PV equals nRT, which means that under ideal conditions, PV over nRT would be equal to 1. So that's our line right here on this graph. All right, now think about it. We said that our standard atmospheric pressure is 1 atmosphere. So in most of the conditions in which we're observing gases in the lab, this is why the use of the ideal gas law is fairly useful, because if you look in this range right here where we would see most of our observations, it will behave like ideal gases. But as you can see here, once we start moving away from that normal pressure range, standard pressure, you can see we start to get a lot of deviation away from that line right there. Okay, and the same thing with temperature. Here we have nitrogen gas at 3 different temperatures. Here is our line at which we have ideal behavior. And you can see that it gets, as we decrease the temperature, you can see the lowest temperature line has the most deviation away from the ideal gas line there. Okay, here we are. Here's the problem I was expecting to see a while ago. All right, so the only calculations that you'll be doing, or that I'm going to have you do here, are some involving Graham's law. You will, in your online homework, you will see some plug-and-chug type calculations with the root mean square speed and with the real gas law, or what we call van der Waals law, which I'm going to show you after we see this. So anyway, here we have calculate the relative rates of diffusion of hydrogen and bromine at the same conditions. Well, Graham's law says is that our rate for the hydrogen, for example, over the rate of the bromine is equal to inverse of square root of their masses. So inverse square root of the mass of the bromine over square root of mass of hydrogen. So we have bromine is, let's see, is about 160 grams per mole, and hydrogen is about 2 grams per mole. And so that gives us, let's see, 160 and square root divided by 2 square root. That gives us about, let me see, it's about 9. So what this would mean is that that hydrogen would diffuse approximately 9 times faster than the bromine would diffuse. Usually when I do these problems and I'm comparing rates of diffusion, I will usually do the rate of the smaller molecule over the rate of the larger molecule. That way, the ratio that you get is going to be a number greater than 1, which means that that's how much faster the smaller molecule moves than the larger molecule. Okay? Another type of problem that you'll see is one like this, where we have, let's see, we're given the rate of 2 of these gases. So I have 24 milliliters per minute for our unknown gas, and methane gas is 47.8 milliliters per minute, and so that's going to be equal to the square root of the mass of methane over the square root of the mass of the unknown. All right, and so the square root of the methane is about 16 grams per mole of my mass of my unknown. And so that's going to be 24 divided by 47.8. So I have 0.502 is equal to 4 over the square root of the mass of my unknown. And so that's going to be square root of the mass of the unknown is going to be 4 divided by 0.502, which is 7.97. And if we square both sides, I get that the mass of my unknown is about 63.5 grams per mole. So that's another use of this, is comparing their rates of diffusion or rates of effusion and using that to find the molar mass of an unknown gas. Okay, here is the actual equation that we use. I know we're kind of jumping topics again. For real gases, in other words, we're at high pressures and or low temperatures, and so we don't have ideal behavior. And anytime you don't have ideal behavior, you use this van der Waals equation. And basically what you can see here is that, remember how we said that the pressures are going to be affected because we've got other molecules interacting with the path of the molecule that's going to hit the wall. And then we also have a corrected volume because the volume of the gas molecules themselves becomes significant. And so we have 2 factors that are introduced into our ideal gas law equation, an A and a B. These are called van der Waals constants, and they are basically values that you look up in a table, and they are specific to the type of gas that you're dealing with. So carbon dioxide is going to have a different A and B value than oxygen does. Okay, so for these, you just have to look them up. And again, I've got in the text and in the online homework, like 1 problem each for you to work through these. But basically, as you can see, this is a plug and chug type situation. And the van der Waals equation is not something that I would ask you to memorize or anything like that. I just want you to realize that it's there. And if I ask you a question on a test, it's going to be more like, under what conditions would you use this equation as opposed to the ideal gas law? Or what types of things does the van der Waals equation take into account that the ideal gas law equation does not? Okay, so really I want you to understand why we would use this more so than be able to use it. But you can go through the calculations and see what are the different results that you get if you use ideal gas law versus van der Waals. So you can kind of see the value in why you might need this in certain circumstances. Okay, and here are some practice problems for you to take a look at. And the answers to these are on the next slide. So take a look at these, and if you have questions, we'll talk about them tomorrow.